At the very beginning, what I want to do is take a look at these two. I'm just going to look at a and b to start. The a is the integral from 1 to 10 of 1 over x squared dx, and b is the integral from 1 to infinity of 1 over x squared dx. And I want you to visualize what's actually happening with both of those integrals. So if I was to say, can you draw me a graph or a picture representing what's happening with the integral from 1 to 10 of 1 over x squared dx? What might we draw? What are you thinking? James? It's a rational expression. Yeah, it's got one of those shapes. Let me draw that in there. So it's a sweeping shape. It's got an asymptote, it's got a horizontal asymptote, and a vertical asymptote at the axes, right? Both the axes are acting as asymptotes for 1 over x squared. And 1 over x squared, because the power is even, happens to always be positive, right? No matter what x value we put in there, it's going to turn out positive. And so the graph has to be symmetric about this y-axis, and all the y values are positive. So this would be the picture of 1 over x squared. Now, if I'm integrating from 1 to 10, what does that mean in words? What am I looking for here? Yeah, go ahead, James.
The area underneath the curve.
I'm looking for the area under the curve. Yep, from 1 to 10. So if this is the number 1 and this is the number 10, what I'm looking for is that area between the curve and the x-axis. That's what that integral signifies for me. Can you guys calculate that? Sure. Why don't you guys go ahead and let's calculate that up. What is that integral? So what is the integral from 1 to 10 of 1 over x squared? I'm going to go ahead and rewrite it as x to the negative 2. Oh, I heard you. You're right. You're right. Go ahead, John. Tell me what you said. So that's negative x to the negative 1, right? So we've got negative x to the negative 1. And then we're going to plug our limits in. And actually, negative x to the negative 1 is like negative 1 over x. So if I'm evaluating this out, what's it giving me? It's giving me negative 1/10 minus negative 1 over 1. Is that what you got? Negative 1/10 plus 1, which is like plus 10 over 10, right? Negative 1/10 plus 10 over 10, which is just 9 over 10. And so we would say that the area under the curve, 1 over x squared from 1 to 10, is actually 9/10 of a square unit. Anybody have questions on that piece? That's normal. We've done those before. In fact, that's a simple integral. What if I was going to draw the picture or look at the second integral? Again, we have our same shape, right? We have asymptotes at the x-axis. We have asymptotes at the y-axis. But if I was to shade or take a picture of this guy, what am I looking at? I'm looking at the area underneath this curve as you go to infinity. What makes this integral different than the other integral is that I have an infinite limit. And when we have infinite limits, we have some funky things that happen. This always blows me away. But sometimes infinite areas, or what look like to be infinite areas, meaning areas that are coming from a function that's approaching an asymptote, that area under that curve as you go to infinity, sometimes that area is infinite, which we would expect, but sometimes that area actually winds up to be a finite number. And it really depends. It comes down to how quickly that curve is coming towards that axis. What is the rate at which that curve gets to that axis? How quickly does it get to that axis? And if it gets infinitesimally close enough, fast enough, then that area actually converges. It's one of those weird things that doesn't make any sense almost, right? That you have a finite area, but sometimes that happens. All right, so an improper integral then is an integral. Well, there's two types, but basically an improper integral occurs when you have a problem with one of your limits. In type 1 improper integrals, the problem is that we have an infinity or a negative infinity. So type 1 improper integrals are defined to be integrals that have an infinity or negative infinity at their limits, okay? So either you're going to infinity or you're coming from negative infinity. Those classify as improper integrals. And sometimes they result in a finite number, and sometimes they result in an infinite number. And we're going to look at all different kinds of improper integrals, and we'll see whether they result in a finite or an infinite. So let's actually evaluate this guy here, and let me show you the steps. Improper integrals are done the same way regular proper integrals are done after you make one initial starting step. And on your test, I will actually say, step 1, write this improper integral as a limit. And everybody will have to show me the following step. You're going to rewrite your improper integral as a limit. That means you're going to assign a dummy variable. I tend to put b's on top. Some people put t's. I put a's at the bottom, but whatever you want. You can put a b, you can put a t, you can put an n, but put a dummy variable in place of infinity, and then set a limit as b goes to infinity. Because we really can't get to infinity, but we can approach it. And so improper integrals are defined to be integrals that have limits as part of limits for their limits, for the limits.
So just to clarify,
Yep, you can put any variable up there. I tend to do b because it's my top one, a for my bottom one, but you can put any variable you want. And so then you would simply, if I wanted to evaluate this, I would simply now evaluate the integral, plug b in, and then take the limit. So I would evaluate this, and we just did it above because you told me what to do. When you add 1 to the exponent, you get -1, and then you turn it over. And so really what you're doing is taking a limit as b goes to infinity of 1 over x, or -1 over x. And so that's the limit as b goes to infinity of -1 over b plus 1 over 1. Ha! And so now, what happens? As b goes to infinity, what does -1 over infinity become? That limit. 0, absolutely. So this is where Calc 1 comes into play, right? Remembering what a limit is and how to evaluate this. So we get the limit as b goes to infinity of -1 over b is 0. That means we have 0 plus 1, and what is 0 plus 1? That's just 1. This blows me away every time to think that even though I don't have a right bound that's finite, even though my right bound goes all the way to infinity, that area underneath that curve approaches a finite number. That just really gets me. When an improper integral approaches a finite number, we say that the integral converges. So when an improper integral approaches a finite number, in this example it approached 1, we say the improper integral converges. And you are going to see this word converges again when we start talking about sequences and series. But that's later in the course. So when an improper integral, go ahead, say again.
That's after break, right?
That is after break. Yep, sequences and series will come after break. It'll be, actually, it's at the end of the course. We're going to do applications now for the next couple weeks, right up to break.
Yeah.
And then after applications, we're going to talk about parametric and polar curves and talk about the calculus of parametric and polar curves. And then we're going to do sequences and series at the very end. So you'll see these words converge and diverge. So if an improper integral approaches a finite number, we say that that improper integral converges. All right, so let's take a look at the next integral, c, which I say is also improper, but it's a hidden improper. The reason I say it's a hidden improper is because there's no infinity that sticks out at you. Why is that second one?
Is it because the negative one and the one are going to have the same value? You put them into x squared? Or it's the asymptote?
Ah, they will have the same value, but it's the asymptote in the middle. You got it, James. The reason why this guy is another improper integral is because even though my limits this time are finite, the problem actually is that there is a value in between those finite numbers where this curve is undefined. So if I was to look at this area, so if I was to visualize what's happening, I'm going from -1 to 1, and again, I'm looking for that area under the curve, and that's exactly why this sucker's improper, because we've got this infinite area that's happening at the vertical asymptote. In type 2 improper integrals, there is a value, there is an infinite discontinuity occurring at some c in the interval of integration. For our example, the problem is happening at 0. And so I would be looking at two separate integrals then. I would be looking at two improper integrals. I could split up the integral from -1 to 1 as the integral from -1 to 0 and 0 to 1, where 0 is my problem, right? That's where I have this vertical asymptote or infinite discontinuity. And you can see it. The area goes up forever and ever and ever. And just like for type 1 improper integrals, sometimes that area will collapse fast enough. So if the curve gets close enough, fast enough, that area will converge to a number. But if it doesn't, then it's said to diverge. So let's actually look at this guy and see what happens. We only need to pick one of these to start. The reason why is because of symmetry. Do you see kind of how I have two sides and they're symmetric? So whatever happens on one side is going to happen on the other side. So I'm actually just going to go ahead and pick one side. I don't care which one you want to pick. Do you want to pick this one? Shall we pick this one? Or do you want to pick the other one? You want to work with -1 this time? Well, I'll pick this guy. I'll pick the second one and we'll work with this. So because of symmetry, I'm just going to pick one side. Alrighty, here we go. So when you have an improper integral, first thing is you recognize that there's a problem with one of the limits. And you have to rewrite, like I said, your first step on your test when you see an improper integral will be to rewrite your integral involving a limit. Oh, let me do it this way differently. This time, I see that my problem is at 0 because there's an asymptote there. So I'm going to let my bottom one be a, but again, like James pointed out, you can let it, John pointed out. I keep calling you James. As John pointed out, you can have an asymptote, you can have any letter be your limit. So I am going to take A, because that's my bottom guy, and I'm going to do this. I'm going to say, let A go to 0 from the positive side. Why did I put that little plus up there? Andrew, do you know why I put that little plus up there?
Because you're approaching 0 from the right.
Oh, I love it. I love your you spoke it perfectly. Because we're approaching 0 from the right when you're going from 0 to 1. That's why we have that little positive side. If I was going from the left, then I would need a little negative side. I love it. And we're evaluating 1 over x squared dx. But we already know what the antiderivative is, so let me write this down. The limit as a goes to 0 from the positive side of -1 over x from a to 1 and what's happening with that limit? Why?
You can't divide by 0.
You can't divide by 0. You can't. But what happens, because remember we're taking a limit, right? You can't divide by 0. You also can't divide by infinity. But the question is, what is happening as you plug 0 in there?
You get really big numbers.
You do. You get really big numbers. If you take, and this is the way I think of it, so I think, okay, I have 1 divided by a, but I'm replacing a with something that's really, 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 really small. So like this number here is 1 over like 1 billion gazillion quadrillion, right? Which is really small, which is going towards 0, 1 divided by approximately 0. But how does this work? When you take division, it's 1 divided by this, you flip and multiply. So really what's happening is I'm multiplying, if I actually flipped and multiplied the denominator, I'm multiplying 1 times 1 gazillion, bajillion, quadrillion, divided by 1, which is why it goes to infinity. So when you divide by something really small, it is undefined at 0, but as I get there, I'm actually going towards infinity. Okay, so what does that mean about this limit? This limit, then, goes technically to infinity, which we learned in Calc 1, we say doesn't really exist, right? or is an infinite limit, if your improper integral winds up and approaches an infinite or infinity or negative infinity, then we say that the improper integral diverges. So if or when an improper integral results in infinity or negative infinity, we say the improper integral diverges. And if an improper integral diverges, there is no value, okay? We say it's an infinite area that's being resulting underneath, but we would say that that integral diverges. So on the first one, we went to a number 1, and therefore we said that this interval converges. The second one went to infinity, and we would say that this integral diverges. And what does that tell us? That tells us that that area just keeps growing and growing and growing. Now, do they always turn out to be convergent or divergent? Yes, but every integral is a little different. We just did the integral on the left, which was the integral from 1 to infinity of, oh, let me go back a second. Hang on a second. Do you guys need this a little more? So in the last class, Leaf, you guys know Leaf? Some of you guys know Leaf. He's on the swim team here. Yeah, he's in the other class. He said, Tina, what about 1 over x? What happens if we change it a little bit, you know? And I said, oh, Leaf, you got my next example. So I want to compare, and I want to look at 1 over x. Does 1 over x have the same behavior as you go to infinity? So we discovered that 1 over x squared converges to 1. That's what we discovered, that the area under the curve from 1 to infinity of 1 over x squared converges to 1. We just discovered that. So the second integral is the integral from 1 to infinity of 1 over x dx. And I want you to calculate that and tell me what you get. And then what'd you get? What did you get when you worked that out? What did you get, Max? What was that? 1 over x? ln of x, right? The antiderivative of 1 over x is the natural log of x, but we still have a limit we're worried about. So we're taking the limit as b goes to infinity of the natural log of x from 1 to b. A natural log of 1 is just 0. But what's the natural log of infinity? What's that sucker? What is that? Do you remember what the natural log function looks like? It's going to slowly keep on increasing. Yes, it is. Yes, it is. It's going to slowly keep on increasing. But as you go to infinity, it's going to be going to infinity. So, even though 1 over x squared converged to 1, 1 over x does what? What does this guy do when it goes to infinity? We say it does it. It diverges. So we say that this guy diverges. Do you think there's some kind of pattern? I wonder if there's something that happens here. So I wonder, can you guys do for me? We might as well look at a couple more while we're at it. Hang on. Can you guys look for me at the following? And tell me, do they diverge or do they converge? What is it that makes it converge or diverge? What about 1 over x cubed? What do you think? What do you think about 1 over x to the 4th? What do you think about 1 over x to the 1/2 power? 1 over the square root of x. Okay, so let's see. Let's divide up and see. All right, so John and Andrew, why don't you do 1 over x cubed for me? Tell me if that converges or diverges. Drew and James, you guys do 1 over x to the 4th for me. Kayla and Max, do 1 over x to the 1/2. So let me give us a little more space for each of them. So you guys just make sure that you matched me. No, the first thing you did was you put a B up there, right? And then you rewrote it, and you guys got, let's see, the limit as B goes to infinity of x to the -2 over -2. So in other words, you were calculating out the limit as b goes to infinity of -1 over 2x squared. So you were looking at, and what did you guys get for that guy? What did he do?
You got 1/2.
That's what I get too. As b goes to infinity, that first piece goes to 0. So you got that this actually converged, right?
Yeah.
Converges to 1/2. That's kind of cool. That's kind of cool that you figured that out. What did you guys get with 1/4? What did you guys get as limit as b goes to infinity? What did you guys get for that guy?
Like the final answer.
Yeah.
1/3.
Did you get that, James? That it converges to 1/3?
Slide it up with, in the little brackets.
Yeah.
-1/3 infinity to the -3 plus 1/3 1 to the -3.
Yep. And then you plugged b in, right?
Yeah, that's what I have here.
Uh-huh.
The plus situation.
Uh-huh. And so you got plus 1/3 at the very end?
Yeah.
Very nice. Very good. That's kind of neat. So the integral of 1 over x squared converged to 1, 1 over x cubed converged to 1/2, 1 over x to the 4th converged to 1/3. Oh, that is too cool. There's like a pattern going on there. What did you guys get when you had a square root of x underneath?
Might have been wrong.
That's okay.
I
No.
got like 2/3.
Well, let's see. Let's see. So what did we do first, Max? What did you guys do first?
Set it to a limit.
Okay, you set it to a limit. And then did you add 1 to your power?
Yeah, we got.
X.
Oh, I subtracted
Yeah.
one.
Did you subtract?
I got 2x over that.
You got 2x to the 1/2. Is that what you got? Yeah, you subtracted, didn't you? Drew did this. Yeah.
What's it supposed to
Add
add?
1 because we're taking an antiderivative, right? This is too cool. I really like this. So this,
Never mind that.
No, it's okay. That's good. So we got 2b to the, I will never mind you then. All right, we'll ignore what you just did. Let's see what happens. So what happens, now, right away there's a difference. The reason there's a difference, and you can't see it, but when you take this antiderivative, all the other times you had x to a negative power resulting. But this time, when I added 1, what happened is this result became positive. And that made x stay on the top. So now, as this goes to infinity, where 2 times the square root of infinity is what? 2 times the square root of infinity is just what? Infinity. This guy's still infinity, right? Like the limit as b goes to infinity, or 2 times the square root of infinity is infinity, right? So what does this guy do? He diverges. Now, what is it that makes it diverge? It's all about the original power. Because the power was 1/2, when I added 1, it made it stay on the numerator. So basically, anytime this power here is smaller than 1, whenever this power here is smaller than 1, it's going to diverge. And so what that's going to do, okay, slow down, Tina, slow down. We're going way too fast. All right, so what's our first summary? The first thing we recognized is, oh, there's a really cool pattern that evolves. When I look at values 1 over x squared, that converges to 1. 1 over x cubed, that converges to 1/2. 1 over x to the 4th, that converges to 1/3. So first of all, I've got a really cool pattern that's emerging when I'm looking at the area under these basic rational functions, which is really cool. All of these converge, even though they're improper integrals. But if we looked at 1/2, we discovered that sucker diverged. And not only did we discover that, but it had to do with the fact that this power here was smaller than 1. And so that actually lets us summarize something. This here, pretty soon we're going to learn something called a p-series. By the end of the course, we're going to be looking at infinite summations that look like this, and these guys are called p-series. So what we're doing right now is setting ourselves up to kind of get towards that idea. But anytime you have an improper integral with a p in the bottom, you will see the following pattern happen. If you're looking from 1 to infinity, you first of all know that it's going to be under one of these rational functions, and you're going to be looking at an infinite area. But whether it converges or diverges depends on the value of p. If p is bigger than 1, then this integral, we discovered, converges. And in fact, we might even put a theory that it converges to 1 over p minus 1, but I'm not going to do that because we didn't do enough to get to that. But anytime p is bigger than 1, this thing converges. If p equals 1, we also did that, and we saw that that diverges. And if p is less than 1, we saw that also diverges. So really, if your power is bigger than 1, then that infinite integral or that improper integral will converge. But if that power is less than 1, then that infinite integral is going to diverge. that has a lot of ramifications later on, and that's why I make a note of it now. But that's it. We just note it. We say, well, that's kind of interesting. And the pattern that erupted for those convergent integrals, well, that's really cool too. But, alrighty, so that's improper integrals. Let me summarize what we stated. So do you guys see what I did? I just kind of summarized what we just did, first of all, for when we have powers. So x to a power, if that number was bigger than 1, that integral converged. If that number was less than 1 or equal to 1, that integral diverged. Dr. Bataki wrote up this really cool integrals. I wouldn't even try to copy this down. This is in the notes. And I'll just kind of say, this tells you a little bit about what we just said. That there's, first of all, improper integrals result when you have problems with your limits. So, if you have an infinity or a negative infinity, then it's called a type 1 improper integral. If you don't have an infinity or negative infinity, but there is an error in between there. So let's go back to the one where we did see at the very beginning, we looked at this one here with negative 1 to 1. And we knew that there was a type 2 improper integral because there was, there was an infinite discontinuity that was occurring at an asymptote. And so that guy is what we call a type 2 improper integral. It's kind of hidden. You don't really necessarily think that 0 or there's going to be an issue, but there is. So type 2 improper integrals are often hidden. They come from finite limits, but there's an issue in between those finite limits. Okay? Or maybe it is that one of the ends causes an improper infinite thing going on. In any case, those are called type 2s, and every type 1 and type 2 will either be convergent or divergent. If the limit's a finite number, it's said to be convergent. If the limit is an infinite value or doesn't exist, it's said to be divergent. So this table, this summary is in your notes online, and you can look at it. But what I want to do is I want to evaluate a couple practice problems. What time? Oh, yeah, we can do a couple practice problems. And maybe just one or two of these. Maybe just one of them. And then I'll give back the tests, okay? And I'll give you a quick survey. So today will be a fast thing. And I'll give you some extra time. Those of you that are doing our recitation today, we're going to take some time to go over the videos, the study videos that we haven't had time to go over. So we're going to talk today about memory, and we're going to talk about how to study for a test. So if you guys are doing my 12:30 recitation today, I'll stop a little early so you have time to watch those videos if you haven't already watched them. How's that sound? I'll give us some time, but let's try one of these improper integrals. Improper integrals they're just like regular integrals, except we have to worry about our limits. I mean our integral limits. So everybody's first step always with an improper integral is to figure out where is there a problem and substitute a dummy variable in, and then go from there. So hopefully you guys are starting and you're saying limit as b goes to infinity. And now I'm going to wander and see what you guys are thinking to evaluate this. Now we go back to everything we studied for exam 1. Can't forget that stuff. How do we evaluate this integral? How are we doing? Let's see. So you did a u sub and you let u equal 3x plus 2. And du is 3dx. And 1/3 du is dx. Did you guys change your limits, or did you kind of just leave your limits be and go backwards? You left them be? Did anybody change them, or did everybody kind of just leave them be? All right, we'll leave them be. I'll leave them be. I don't know what Dr. Soltis did. Did he usually leave them be, or?
I also don't remember.
Don't remember? Yep, no worries. So if we're going to leave them be, then I'm just going to put bubbles there to represent that we've got some limits, but They belong to x's, not u's. And so they're going to kind of stay in my periphery vision, but I'm definitely not going to put them on my integral because otherwise I might be tempted to stick them in place of u, which would be a bad thing. So I know I have limits, but I'm going to kind of keep them in a thought until we're ready to work with them. You guys, this is a -2. This is easy, right? We've got the limit as b goes to infinity, and you guys got -1/3 u to the -1, right? And then when you replaced your u, that's with the x, that's when we can stick those limits back on, because now we're like, okay, now we got our x's back. And so let me see if you guys are getting the same thing I'm getting. Plus 1/3 times 1/3 times 5 plus 2. Questions? Did you guys get to that? Did you guys all get there? Wait, what did you do then? What did you say? Drew, what did you say then? What happened?
Well, I did it like I had the 3 out, like I just
Out
put
front?
all of them
Okay,
together.
perfect.
And then I just
What did he go to for you?
0.
He went to 0. Good.
So then you just get 1/.
So then you got 1/3 times, and then what was that guy? 1/17. Beautiful. That's a finite number, right? Did you guys, you can multiply it. You don't have to multiply it, but if you multiplied it, you would get 1/51, right? And so if WebWork or I asked you on a test, does this converge or diverge, what would you say? Converges. It converges, it converges to a limit. It's in math, we use that term to say it goes to a finite value, a limit. Yeah.
Should we go back and fix our what was it left up there? Or
Where did I mess up? Did I mess up?
The spaces that we left open as limits.
No, I'm going to leave those. The reason I leave them, James, there's 2 things we can do. I leave them because what happened was I went from the dx to a u. And so that b and that 5 were x limits. And so I kept them in the back of my mind until I replaced and went back to x. And then I put them back in.
Okay, so we don't actually need to put anything there.
You don't have to put anything there. Now, so this is my thinking. So this is what happens. Students sometimes don't put anything here, and instead they put a B and a 5. And then they get to here, and they plug a B and a 5 in here,
Yeah.
and then they get the wrong answer. Because that U doesn't deal with the B and the 5. So I put them there to say I have limits. I know I have limits, but they're not the right limits. I have to wait until I go back to X, and then I put my limits in. Now, in our class, in Calc 1, we did it 2 ways. We did it this way, where we ignored our limits for a little bit, but then we also did a change a limit. See if this makes sense. See if this looks good, James. So we also, I don't know if you remember because it's been a long time, but we also did something like this, top U and bottom U. And what we did was we practiced a couple problems, not a whole lot, but just a couple problems where we changed our limits. And we said the top U is when we take this top number, and I remember doing it with like pi over 2s. We were doing pies and things. Do you kind of remember, like we plugged some pies up here and stuff? So the top limit is when you take those numbers and you put them in place of b. And if you put them in place of b, then you could rewrite your integral with those new limits, 17 and 3b plus 2, and you could rewrite those directly on your integral, and then you could work it out from there, because what you've done is you've changed to have u limits. Now, some people like to do that, some people don't like to do that. I like to do that, so I always do that, where I change my limits right away, but most students tend to not like to, and that's why I put the bubbles in. All right, I'm giving everybody a headache. Go ahead, John.
It's due Thursday.
It's due Friday now. I pushed it back, yeah?
Can we start some of it? Or
Absolutely start some of it.
Okay.
You can do everything
Will
on
there
that
be a technique
homework.
that we need to learn for?
The only thing that we are going to practice on Wednesday, which you don't have yet, is L'Hopital's rule,
Okay.
which comes from Calc 1, okay? And my class, you did that in recitation if you went and saw Bogdan and Professor Montgomery talked about that during their lab day.
I missed that one.
If you missed the day. So the only thing you will need that we haven't talked about that we're going to talk about on Wednesday is called L'Hopital's rule. And so if you want to go back and remind yourself what L'Hopital's rule is on a video or something,
Yeah.
but we'll do it Wednesday. That's the only thing you need that we haven't talked about for the homework. Otherwise, start the homework. 1,000% start the homework. And in recitation today, if you're coming, you're not coming today,
I'll go Thursday.
we'll probably do some practice with L'Hopital's rule to get ready for Wednesday. Okay. Yep.